Okay, good morning again. It looks like so everybody's already here. And the first things I put the slides, these presentations on the general channel in Slack if you want to download it. Yeah. So today we are going to go beyond what we have learned and practice on Monday and Tuesday, and so we call it here advanced data parallelism with deep speed, which is a library we're going to see later. And yeah, we're going to see new ways of doing the data parallelism. And we're going to start with this presentation, and we're going to do a couple of tutorials with deep speed. And at the end of the session, you're going to work with Enrique with the lining library of PyTorch, which is another library for doing distributed training with PyTorch. And in particular, you're going to see how is the deep speed integration of PyTorch lining. Okay, so so far, what the kind of data parallelism that we saw these 2 days. So the first thing that we can notice is that this does not reduce memory per device. That it is possible to increase the batch size and spread spread the training all over a cluster, and you could you could regulate the amount of batches and that you send to every worker in the cluster. But if you're in a situation that the model cannot train because not even with batch size equal 1 in your cluster, there is nothing that data parallelism as we saw it can do. Okay, and the other thing is that in the last 2 years, there has been appearing many models, mostly based on the transformer architecture, that they have they have a very large size, in the order of billions of parameters, and more than 1.5 billions of parameters. It does no longer fit in the current GPUs, not even in the more expensive one, more advanced, with the 32 gigabytes of memory. And the thing is that these models, they are really showing a significant accuracy gains compared to other models in the past. So it may happen that they are going to be a trend. This is going to be a trend to have this such a large models for I don't know, for many tasks in deep learning. So alternative to data parallelism, there are other options. There is model parallelism. The model parallelism is well, it's exactly what it says. The model is parallelized. The model is spread over the cluster instead of only the data. So in this case, data parallelism. Let's remember that we have a copy of the model in every GPU, and the only thing that changes is that different data goes to different GPUs. Okay, in model parallelism, the model itself is split and in multiple GPUs, but implementations can be quite complicated and can be model specific, and it does not give in general a good performance. It sort of does a trade of performance for saving memory. So, you lose performance, but you gain the possibility to feed a huge model in a GPU or in multiple GPUs, which otherwise you couldn't. There is also the option of pipeline parallelism. And pipeline parallelism is something similar to I would say it's a case of model parallelism, but the idea is that the model is split by layers of chunks of layers and over the GPUs, and then the execution of the training is going to happen in this way. So the first layers that are in the, let's say, the GPU 0, they are run while the rest of the GPUs are doing nothing. Once these layers are calculated, these results can be passed to GPU 1, and now GPU 1 is calculating, but the rest of the GPUs are doing nothing. So this is not this is not an optimal setting, because in general, as we saw before, all these days, we want to have the GPU always calculation. This is what always calculating. This is what gives us good performance. And there are ways of decreasing the time that the GPU is idle in pipeline parallelism, but only that. So only ways of decreasing it. There is always a time that the GPU is not going to. Some GPUs are not going to be running. Okay. And so, having said that, we are going to, in this session, we're going to show a rather new solution that is within data parallelism, but you will see with very clever optimizations done to it. So this is done by the deep speed library that we're going to introduce in a minute. And then within deep speed, there is something called Zero, which stands for Zero Redundancy Optimizer. That is mostly the part of the library that is in charge for doing these smart things I told you about, that we're going to see in a minute. And yeah, we're going to do a demo, which we're going to run a 3 billion parameter model on Piz Daint. So it's a Z5 model transformer from Google. And at the end of the presentation, the tutorial that we're going to do is to understand the effect of this zero. Well, there are different stages of zero. I haven't said it yet, but on the memory during training and during how the model is going to be loaded. Okay. So let's start. So first, deep speed. So deep speed, as I said, is a library that is used for distributed training, but we will see that is even much more. It is an open source open source library, and it's developed by Microsoft. And the idea of it is that it is intended to reduce the computing power and memory use. And memory requirements to train, say, particular very large models. Okay, and yeah, the idea, mostly the idea is to leverage the software. Sorry, I have there is a noise outside. Let me just close the window. Just a second. Okay, sorry. So the idea of deep speed is to leverage the same GPUs, the same cluster that you have, and being able to run these very large models, which otherwise you would have to go to change hardware, and sometimes not even like that. Okay, and we're going to be later seeing the features, but one of the things is that it has mixed precision training, and that's very easy to turn on and off. It enables single GPU training of even large models, and also multi-GPU and multi-node training. And with this zero component, yeah, it enables training up to around even just to models in the order of 100 billion parameters. Okay, so and zero. So zero is something that belongs to deep speed, zero redundancy optimizer. The idea of it is in this part of the library. The idea is that it enables partitioning various parts of the model training. Sorry, not the model. Of the training states, like weights of the model or gradients or optimizer states across devices, and like that it allows to save memory. Okay. And zero is implemented in 3 levels that they call stage. So stage 1 is the partitioning of optimizer states. So for optimizer states, for instance, in Adams, they call the 32-bit master copy of the weights, if you remember from yesterday in the mixed precision lesson. And also the first and second momentum. Okay, and they can be in zero stage 1. All these quantities are not copied in all the GPUs, but instead they are spread over the GPUs. The stage 2, so the level 2, also contains the stage 1. It includes also the partitioning of the gradients. Okay, so now the gradients are going to be spread over the nodes. So no single node has all the copies of the gradients. And later in the presentation, we're going to see that this is partitioning the gradients is something that comes naturally after the stage 1, after the optimizer states are already partitioned. You will see why. And the stage 3 is the more aggressive, which is the partitioning of of all these 2 things, stage 1 and stage 2, but also the model parameters are spread over partition over the different GPUs. And this one in particular is one that allows to fit really large models on the GPUs, which otherwise just doing model equals the model would crash, would go out of memory when you try to run it. Okay. So most of the things that we're going to see today with zero are done for the Adam optimizer. So we're going to have a quick look to it. And so we choose this one because Adam optimizer is one of the most popular and most common you will be using in training, for training your models. Okay, so let's not pay too much attention to the math, but the idea of Adam optimizer is that in every iteration step, these 2 quantities, the first and the second momentum, are computed. So the first momentum is computed like this. It depends on the weights on the current step and the previous values of the momentum. And the second momentum, same thing. It depends on the current gradients. Sorry, I said weights. I think the current gradients, but the second momentum is square, and the previous values of the second momentum. And these beta 2 and beta 1 are constants. So these 2 things are calculated once the gradients are available. And with these 2, with the 2 momentum, these 2 magnitudes are computed, and the update is done like this. So current weights is equal to the previous weights minus learning rate times this value that depends on these 2. So the idea is the gradients are computed, the momentum are computed, and then with that the model can be updated. Okay, so this is Adam optimizer. And the logic behind doing all this is that if the training goes to oscillatory, so it's moving in the loss surface very oscillatory. This helps to reduce oscillation in the directions where the oscillations are happening, and accelerate in the other direction. Okay, so it allows you to converge faster. So having known that, we can start seeing what zero does. How's the breakdown of memory of applying zero to your problem, to your training. So first here, let's see the memory breakdown with the Adam optimizer. So there are in mixed precision, there are the gradients and the weights in FP16, right? And each of them, FP16 is 2 bytes. So all the gradients is going to be 2 bytes times the number of parameters. I call it P, the number of parameters of the model. So there are these two things. There is the master copy of the weights of the model, of the parameters, which is in FP32, and this is 4 bytes per parameter, so 4 times P bytes. And there are the two momentum, the first and second momentum, in FP32, which is also 4 bytes and 4 bytes. So in total, if there is no zero, just data parallelism as we saw before, the total size is, summing all this, is so 2 and 2, 4, 4 and 4 and 4 and 4 is 16. So 16 times P bytes. So this is what the model plus Adam optimizer in mixed precision is going to occupy. And of course, there is extra memory that is memory from activations that it will depend on the batch size. There are buffers and things for temporary calculations, and it can be they can happen also fragmented memory that is unusable in the GPU. Okay, so 0, 1 is the sum of all these sizes. So I put this bracket here to represent the size of the elements. Now 0, 1, we said that the optimizer states are going to be a partition, and the optimizer states in the vocabulary of in deepest speed, they call these 3. So the master weights of the copy in FP32, the first and the second momentum. So this one are going to be divided by n workers. Okay, so the second stage 0, 2 is this 3, the same, plus the gradients in FP16, and in 0, 3 everything here is going to be a partition over the GPUs, and that's it. And now we can see an example. Let's consider a model with 7.5 billion parameters and 64 GPUs. So here, remember, this is 16. We get 16 bytes times 7.5 billion. We get 120 gigabytes. So if we want to train this model using Adam, we need 120 gigabytes available only for this. On top of that, there are all the activations and temporary buffers are also needed. So it's a lot of memory. Of course, this one with data parallelism, as we know it, let's call it regular data parallelism, there is nothing we can do. Okay, so if we apply 0 stage 1, so these two are not shared, it's only the model states, and this is 13 divided 64 is around 0.18. So I put here 0.2 times 4 is 4.2, and 4.2 times 7.5 billion give us 31.5 gigabytes. And 0.2, so all this, no, this one and these ones are a partition. We get 2.2 times 7.5 bytes, so 16 gigabytes. So we're getting here closer to a size that will fit in the GPU, not on Piz Daint, because on Piz Daint we have 16 gigabytes of memory in the GPUs, but other modern GPUs that can have 32. Now this one can be possible, probably depending on your batch size and how much extra memory is used. But here we already can fit the model can fit the training, sorry, on the GPU. And finally, the 0.3, we get a factor of 0.3 when we divide all this 16 by 64, and it gives us 1.9 gigabytes. Okay, so and so we can have here we can even fit it on our GPUs on Piz Daint. Sorry. So I saw there was a question. And okay. So let's see a bit how this is. If there are questions, let me check it in the chat. No. So if there is a question, please raise your hand or unmute and ask. Okay, let's see how this works with during the training. So here I put 0, 1, 2 as title, but we're going to have in mind first 0, 2. 0, 2 again. Let's go back. Is this one? So the model states plus the FP16 gradients are partitioned. Okay. So let's start with 0, 2, and let's see that now a training step has started. So here we're going to use also data parallelism. So every GPU, so this is one GPU, this is one GPU, this is one GPU, they are going to receive a different batch. So batch 1 goes here, batch 2 goes here, batch 3 goes here. Okay, and here we represent the memory. So those are the arrays of those are the gradients. These are the second momentum, first momentum. This is the master weight of the copies. They are here, and this is the master copy of the parameters, and those are the parameters in FP16. Okay. So this one here in the middle squares, they are the model states that they are going to be partitioned both in 0, 1 and 0, 2. Okay. So at the beginning of a training step with 0, 1 or 0, 2, the memory is going to look like this. The first part of the first layers, let's say, of the first arrays of the model are going to be in GPU 0. The second group in GPU 1, and the third group in GPU 3. Okay, this is clear. And okay, and so let's say that this one is the closer to the left is the first layers of the model, and the closer and the latest layers are the vectors corresponding to this part. Okay, and yeah, so if the batch comes, you will find the model like this. So the FP16 weights are there, so the forward pass can be calculated. So we get a loss, and when the loss is calculated, the back propagation can start. So the first step of back propagation is going to happen like this. This part of the model, so this session of the weights, is going to be calculated for the different batch sizes in every GPU. Okay, so remember there are three different batches. So for three different batches are going to be calculated. So the weights are the same everywhere, right? But since the batch is different, it's going to give different values of gradients. Okay, And now what is going to happen is that these two workers, these two GPUs, are going to send their values of this session of the gradients to the GPU 3, and they're going to reduce it. So here there is 2 and 21, and now these are summed. So there is 24 plus 46 plus 2, and this one 1 plus 15 plus 21, and this is the value of the final value of the gradients. Okay. Then at this point, after this is done, these gradients can be deleted, and the backpropagation continues. These are calculated again. Different batches give different values, and now these two workers send to the worker in the middle their values and reduce them. So before we have 21 and 24, and now we add these two, and yeah, there is 79 and 27. Now same thing, these two can be deleted, and the backpropagation continues. And again, different batches give different values of gradients. Now the last one sorry, these two sends to the first one and reduce. So before there was 3 and 46, now everything is added, and the other thing can be deleted. So at this point, these three values here, the average can get we can get the average from it, and those are the gradients. So the gradients are completely calculated, and once the gradients are calculated, remember that the two momentum are calculated. So we update it. So we put this star to update the momentum. Okay, and since so this worker doesn't need it's not going to update anything here, because there is no momentum corresponding to these layers here, to this part of the array. So this one updates only this part, this one updates only this part, because there is nothing else. Okay, so the momentum can be updated, and once the momentum can be updated, the weights can be updated. And now, as you see, the weights are updated, but only on the section of the array corresponding to every GPU. So this one updates only these two, this one only these two, and this one only these two. Okay, and now, as you expect, there has to be another communication. So the weights are going to be sent here. So now it's not reduction; it's just sending to so all of them have the same copy. Same thing. This one sends to these two, and finally this one sends to the previous two. And at this point, all the weights have been updated, and the next step of the training can continue. And that's it. That is how 0.2 works. And I was saying at the beginning that 0.1, that 0.2 is a natural addition to 0.1. The thing, a very important thing that that happened here is that this data, it doesn't need to be communicated. So there is no need to have this data in the other GPUs, because the updates that we care are the communication of the models and the communication of the gradients. But with doing these two things, yeah, the training can happen without having to communicate these two. And the thing is that in 0.1, that the gradients are all in the same. Sorry, all of them in all the GPUs. So there is no, these empty spaces are not there. The thing is, in 0.1, even if having the gradients are there, the weights cannot be updated, because the momentum are not in all the GPUs. So 0.2 is hence 0, 1 doesn't have any, doesn't do anything different to 0, 2. It's just, it needs the same kind of communications, okay? So 0, 2 is natural to add it because the synchronization of the reduction of the gradients and the synchronization of the weights need to happen anyway. Okay, and in summary, how the training happens is that each of the workers communicates with the rest of the workers 2n-1 times. So remember that each of them needed to send their gradients 2 times to the other workers. So in general, the number is 2n-1, and the first the first n-1 are the gradients. That's just what I said. I'm sorry. So n-1 is the gradients. Remember that every worker sent twice the gradients, and the second n-1 are the communication of the weights. Okay, so the total amount of data sent by each worker is 2n-1 times the size of the chunk that is sent. Remember that the array is not sent completely. Is the size of the array that we call phi, the size of the array, divided the number of workers. And for large n, this is almost 1, and the total amount of data sent by worker is 2 times the size of the array. And if you remember, this is the same of that in data parallelism. Data parallelism, regular data parallelism. Remember this, that there were in this case 3 sends and 3 reductions and 3 sends, and at the end we said that each worker sent 2n-1 times, n-1 for the reduction, and n-1 for the sends, and the total amount is exactly the same. So in normal regular data parallelism, and in this kind of parallelism with 0, the amount of the volume of communication per worker is exactly the same. But just pay attention to a difference is that one worker will be receiving and sending to all other workers, in this case, like here, okay, or like here, while in this one, every worker only connects with 2 workers. So in this one, if you have 512 nodes, the worker 0 or the worker 500 is going to connect only with 2 nodes, while here this worker, to do this send, it has to send a large volume of it will have to send to many workers at the same time. Okay, but the volume is exactly the same. And okay, we can continue. So now I propose to make to stop to go out a second to this link that I will post it in the chat right now. So this link it explains it's a video that explains how 0.3 performs a training step. I think it's a very good video and really helps to understand 0.3. And yeah, I just didn't want to repeat it do new slides for the video, because the video is already very good. So the video is inside of this post, 0 and deep speed, new system optimization, enable training models with over 100 billion parameters. And this is done by the deep speed team. So the video is around 5 minutes, but it has a lot of information, and you may have to stop and read, And I think 10 minutes we can come back and discuss the 0,3. Okay, so I'm going to stop here. Okay, we are back. So I hope the video was useful for you. I like it very much. And so here from the video, you can see that the same thing is already is quite similar to what we saw, except for the part that we can go back. That these weights here are also distributed. So these parts are blank, and the thing is, in 0,3, each of the workers we will communicate with the rest of the workers for the n-1 times for the reduction of the gradients. Okay, this part is the same as in 0, 1, and 2. However, this update of the weights that 0, 1, and 2 does at the end of the training step, that one doesn't happen like that in 0,3. In 0,3, in the forward pass, since always the weights are needed by every worker, every parameter, every weight is sent n-1 time by every worker during the forward pass. So n-1 times during the forward pass, and n-1 times also during the propagation, because they are also needed. And then, so putting all this together, n-1, 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 we get that the total amount of communication volume per worker is 3 times n-1 times the size of the array divided n, because it's always still a piece of the array. And this, for big N, this is close to 1. And so we have the communication volume per worker is 3 times the size of the array. And remember that in regular data parallelism and 0, 1, and 2, this value is 2 times the size of the array. And in this case, we get 3, so it's 1.5 times the data parallelism with the regular data parallelism, or 0, 1, and 2. Okay. There are questions here? Okay. So more on deep speed. More on deep speed. Now, before we're going to see how it works in practice. How you can incorporate it in your code. But so it has a very easy feature of turning on the mixed precision training. You will see now. It has a version of 1-bit Adam optimizer. So 1-bit Adam is a modality of doing Adam where the first steps, so the training starts like regular Adam training, but as I said, after a certain point, the gradients that are sent are compressed to 1 bit, that means sending only the sign of the gradient. And they managed to write it for Adam in a way that it can give the same convergence speed than Adam. It used to work. It used to exist already 1-bit stochastic gradient descent, and deep speed implements same thing with some tricks for Adam. Okay. Deep speed also has something very important, which is zero offload. That zero offload, it offloads memory and part of the computations from the GPU to the CPU, and that one enabled to train really large models of the order of 10 billion parameters on a single GPU. Okay? And zero I think this one I'm sorry. I think this one I wrote it wrong. This was deep speed. Deep speed performs on the fly memory defragmentation. So that means that sometimes in PyTorch, PyTorch itself creates pieces of memory that are not contiguous. So it creates some array here and some array here. In the middle, there is a small piece of memory that is not used. And all these fragments of unused memory, they cannot be reused. And Zero on the fly has an option to put together all the memory and defragment and recover, so reclaim GPU space from some memory space from the GPU. Okay. And we have seen that Zero is being implemented natively now in PyTorch. You can have a look to this class Zero Redundancy Optimizer. And we put an example for Piz Daint based on a tutorial of PyTorch on the repository of the course. And I think I wrote it at the beginning, but I think I didn't say it. Zero works only for PyTorch. I don't know if it is right now, or but maybe it will be implemented not in deep speed, but maybe in other packages as well. That's it. And so that's it for the presentation. Now let's go to the notebook. But actually, I will go to the notebook, and I think I better show you this example because it will take some time to run. And yeah, and yeah, later you can follow yourself. But here, what we're going to do is we're going to train this T5 model I mentioned before. And this model has close to 3 billion parameters. That is according to the calculation we did with the for Adam optimizer with mixed precision, with a regular data parallelism that we had this factor of 16. We need a minimum of 48 gigabytes with an optimizer to do the training, plus all the activation memories and data buffers and etc. Okay, so this one we cannot do it on a single GPU. And so we are going to see to use 03 with CPU offloading for that, so to do it on Daint. And we're going to train it with the data set. Data set is called XSUM, that comes from summary. And the data set is pairs of news articles with their summary. And then we're going to train this model to give, it's not trained, it's actually fine-tuned because it's already pre-trained. We're going to fine-tune this model so we can give it a news article, and it will output a summary. And this is not like the Q&A thing that we did yesterday with BERT. So this is going to really generate text. It's not extracting just verbatim text from the input. Okay, so we can go to Jupyter Lab, and let's have a quickly look to the model. So it is okay. It is 10. So there are different variants that of the model that you can get from Hugging Face. There is T5 small that has 60 million parameters. There is T5 large that has 737 million parameters, and there is T5 3B that has 2.8 billion parameters, so close to 3 billion parameters. So here in the notebook, so you will have to pull from the repository to Face's notebook we put in the morning. So this notebook, just going quickly. So, going quickly, it's very similar to what we saw yesterday in with BERT. And so we were going to use Hugging Face, and then we created tokenizer, as we know already from yesterday. What is it? And we get a model from Hugging Face. So we're going to start with T5 small. Of course, we're now using a single GPU. If we put T5 3 billion, it's not going to fit. But we're going to go to that in a bit. So doing like this, you can print the number of parameters. So we load the data, and okay, yeah, and so we set some parameters for the data for the training here. This is something to process the data to create the training set. Same here, we are creating the training set, and yeah. So this data, by the way, you should already have it on your student account, but this one will download it automatically anyway. And okay, we're here again. More things. We have an optimizer. We move the model to device, and then so if we see here, this is not the GPU memory, but here we see that we are using at this point. So when we created the model, there was 2 point something gigabytes, and now it moved to 4.4. And that's it. We can do the training. I did only 10 steps, so it stops quickly. So this is not really fine-tuned. This is the evaluation. We're going to use a metric that is used for natural language processing. That's called the Rouge metric. And so we evaluate, and we get the value of the metric at the end, I think. Yeah, but this doesn't make sense because the model is not tuned. And the idea, it will give something like this: summaries, and I think here I'm printing, predictive summaries and reference summaries. But you see, everything is mixed up. It is not trained. Okay, so now just for to see what happens to let's put here. Let's see, kernel, restart kernel. So we restart the kernel and we set the memory. We reduce the memory here. We have, it says, 200 megabytes. Let's see what happens if we put T5 3 billion. So 3B. This one we don't need for what I'm going to do. So here we are loading the model, and just let's have a look. This is we're not passing it to the device, to the GPU. This is only on memory of the CPU memory. And so look at here the memory consumption. So this one I already downloaded, so it is faster, but otherwise it will take some time to download. So we got here 22 gigabytes only for loading the memory, this model in memory. And so here we can print the model. So we see it's almost 3 billion parameters. Okay, so we can we can stop the thing here. Restart kernel. Okay, and before trying to run this one on Daint, let's have a look to. I think here. No, this is the video. Okay, So this is our repository, and let's have a look to how deep speed is used in practice. So for things is we use you can use a JSON file to pass configuration values to deep speed. So here we define like this. There are many options, very customizable, but this is a minimum one to not overwhelm you with the details. But in this file, one can pass the batch size. This is here will be the total batch size. If you have 16 GPUs, one batch equal one is going to go to every GPU. So this is the total global batch size. It allows do gradient accumulation. So you can put here in gradient accumulation is that it won't synchronize over the workers the gradient in every step, but instead so there will be many batches going, and the gradients are going to be stored and averaged within a single GPU, and then after a certain number of steps, the communication is going to happen. So this one is used to reduce the amount of communication that is needed. But here we put one, so it's going to happen as we have seen every single step. So this is print stuff, login details. So you can push the optimizers, and this is the first thing. So the optimizer is not defined in deep speed in your script, but it's defined here in the JSON config. And this here will be an optimizer from deep speed or from PyTorch. Okay, so the learning rate, and there are many other parameters that you can do. So FP16 training is as simple as adding this dictionary here, true or false. And adding the zero optimization is as simple as adding this part here, and you would have a stage 1, 2, or 3, and then in this case we have a stage 3 with a CPU offload true for our big model. Okay, so this is the JSON. Of course, again, every of these steps, like of these fields, like the optimizer or zero, they have many other configuration parameters that you can play with it. But to start, I think it's better to start with the defaults and then slowly learn what each step, each parameter does. So let's have a look here to deep speed. So deep speed is very similar. Simple is basically just PyTorch code with a couple of lines added. So here we import deep speed, and if you have a parser with rparse, you can wrap it with deep speed add config arguments parser, and then this one will enable the possibility to pass in a command line option the command line option for the JSON configuration. Okay. That's it. This is the first thing. The rest is actually we can do like this: deep speed. No, deep speed. So this is the first thing. But this one you don't have to do it always. You can pass the config directly to the next part that we're going to see. So this is the first thing. The rest is, you see, PyTorch code, nothing to do with deep speed. And this is the other thing that you have to do with deep speed. So in this deep speed initialize. So deep speed initialize is going to initialize the PyTorch distributed. So here you don't have to do the initialization of these environment variables as we saw yesterday. And this thing, model, sorry, the deep speed initialize. So you pass the arguments, that the arguments will contain the JSON configuration, the model, that the model was created, it's a normal model by PyTorch, the model parameters. The model parameters can be obtained again from PyTorch. Here we do it. Model engine. Let me just quick. Okay. Here they are defined this way, but they come from model name parameters. They come from PyTorch. So let's continue here. And model parameters and the training, the data set. This is not the data loader. This is just a data set. So here I have a data loader, but it's not really used. And here this is because in this in this particular data set, it needs an extra function that is going to act in the batch before the batch is passed to the training. Okay, but this one is optional. And that's it. If you see there is nothing else of deep speed. The only thing is this one. So model engine. Now the training, you have model engine device. So this is nothing. And the training, you wouldn't do loss dot backward. Instead, you would do model engine dot backward, and you will pass the loss. And instead of doing optimizer step, you would do model engine dot step. And that's it. This is very simple. And if you look here, the optimizer comes from this part. There is no optimizer defined. The optimizer was defined by the JSON by the JSON file. Okay, so let's so it's 10:15. Maybe we can take 15 minutes break, and we can go to and later we see how to run the model on this big model on Piz Daint. Okay, so yeah, let's meet again at 10:13. Okay, sorry, at 10:30, 10:30. Okay, we are back. So now what we're going to do was to check to run the example. So let's go here to the repository t5xzoom, but just please follow the screen instead of doing yourself, because yeah, I think you can do it later, but better. So here we have this T5 text summarization deep speed that we saw before, and we can try running it with different levels of 0. So I have so this one. So let's start with 0, 0, which 0, 0 is not 0. So there is no 0 here. So we are going to use a batch size 16, and we're going to enable FP16. So let's run. It takes some time. So if there are questions in the meanwhile, please unmute yourself. Okay, didn't I didn't think too much very well this. I should have maybe done something alternative because it takes a couple of minutes to start maybe. So here we are using four GPUs, okay, and so deepest speed 0, what we are going to do now is yeah, the regular data parallelization, what we saw yesterday and Monday with PyTorch. So it's starting, but this is just downloading data. And now it says, you see, initializing torch distributed with backend nickel. And here it says discovered MPI settings, word rank 0, word size 4, and rank 0. Okay, so word rank 3, 2, and 1, and this is local rank. Do you see this line here? Not using the deep speed or torch distributed launchers. The deep speed has a launcher, but it doesn't support Slurm as far as I know. So we don't use it. We just run it as we did, like a normal thing, run Python JavaScript. And that's why he said not using this one, attempting to detect MPI environments. But here on Piz Daint is fine. He finds our ranks. You see, so 0, 1, 2, 3. This is our rank. So everything is fine. It starts nickel. We continue. All this info. No, wait. So this nickel info. This is information from nickel, and here we know that the nickel in fact is being initialized and it's working. What else is important? All these things. Okay, this is more nickel. This is data from deep speed. You see, there are many other parameters that we use them as defaults, but yeah, we have many other things. So this is the what we pass. Oh, I'm sorry, by mistake I pass 0 optimization 3, stage 3. I ruined the suspense because I want to show you first stage 0 and see what happens, and then stage 1, 2, and 3. But I started by the last one. Sorry about that. So this is stage 3. So stage 3, we see that the memory allocated is 12 gigabytes. So this is the memory with the already spread by device. So every device is going to be 12 gigabytes. Remember that when this estimation that we did is estimated by 3 billion parameters gives 48. So this is approximately that divided in 4 GPUs. Okay. So at this point, there is only memory allocated and not too much else. This is just I'm printing this in just after the initialization. And now this thing fails. So as we see here, and I'm sorry, I am sorry. This is sorry. What I said was I got confused. I'm sorry. This is the memory after the allocation. What I said was what is going to happen later. So we have 12 gigabytes after the so after just allocating the model plus some other stuff that deep speed can put in the memory, but that's it. And now we see that just right after that, it crashes, and when we look at the end, the error is CUDA out of memory, and this is happening because even deep in this amount of GPUs that we are using, even as partitioning the model through the GPU is not only the model, it's G03, so partitioning everything through the GPUs doesn't give enough memory to do the training. So you can allocate the model, but the training cannot be done. So for that, we have to do. We would have to make it work the training. We will have to go a step further, which is to add here to series 3. We can add CPU offload. So CPU, this option is only available for stage 3, if I remember right, and I think it's available only for stage 3. I think if you use try to use stage 1 with CPU float, I think it doesn't work. But now I'm not sure. But anyway, so we use stage 3 with CPU offload, and we try again. Let's run. So we change here the config. We wait a bit again. Okay, it started. Check. Okay, now you see a CPU offload true. Let's check the memory. The memory is, okay, so the memory, remember last time without the offload was 12 gigabytes. Now we have 5.7 gigabytes. And now the training is happening. You see, so this is the training. And this line here is because of the mixed precision. So it's trying to scale the gradient, but it's using a scaling factor that is too big and it's going overflow. So here you see it is reducing the scaling factor. But yeah, so now with these two these things with the CPU flow, the training we can do it. Okay, so we have here. So Zoom is blocking my screen, but you see step 10. So it is it's doing the training. So maybe we can stop it here, and just even I ruined the big surprise how you can run it. So we can go back and try to run it with DS sorry, with 0.2 and see what happens now. So 0.2 has no no partition of the model and no float. So here remember 0.2 is the FP16 gradients and the momentum and the other momentum and the master copy in FP32 of the weights. In the meanwhile, since we are waiting, I would like to remind you that these student accounts that you have, they will be available until tonight, I think, and so everything is going to be gone tomorrow. So please, if you want to save something that you wrote or some changes that you did, move it to your normal Piz Daint account before the end of the day. Okay. Okay, so it finishes, and as expected, it crashes with CUDA out of memory. Let's see what happened. So we get the nickel information that we saw before. And if we look here, loading extension module, this line that we were looking before that was the after the loading loading the model that with 03 was 12 gigabytes, and with 03 with CPU offload was 5 gigabytes. Now this line doesn't even appear because with 02 and of course by extension with 01, the model doesn't fit on the GPU. So time to load, so it crashes directly after not after, while trying to load the model. Okay, and yeah, that's it. And now I can go back to the presentation. Okay, I'm in the presentation. Let me move this thing off Zoom. Okay, that's it. I hope this was useful for you, this demo. And because if you are in the situation that you have to run such a big model, this is a good solution that you can go to apply 03 and CPU offloading. And of course, this thing is more for need just to be able to deal with all this memory and not really to speed up the training. Okay. And so finally, here I can give you 15 minutes. There is this is exercise, and yeah, you don't have to do it now. You can do it later in the day, because in the afternoon the accounts are still going to be able and available, so the reservations. But one good exercise that we wanted to propose you is to go through a table like this. And sorry, I didn't explain well the exercise here. I will update the slides. I'm sorry about it. But what we want to propose you is to use the same script that we were just running, and get a table like this that you have a number of nodes, batch size that you are using, number of parameters of the model, and get the memory after the model is updated. So that this is the memory we were looking at, and the memory during train, that it will be printed if we leave the training run a bit longer, and the zero stage. And we wanted to propose you to go through the model T5 small, that is 60 million parameters, the model T5 large, that is 700 million parameters, and this one, the model 3B, this 3 billion, and fill this this table. And the main idea of this exercise is to understand the effect of every zero stage 1, 2, and 3 for different kind of models. So what will happen with something in the 100 million parameters range, which is yeah, the T5 small is there, but also models like convolutional neural networks like Inception or ResNet 101 are in this range. And this one can give you, at least it gave us a very good idea of what to expect and for different cases with zero. So I will give you 10 minutes, not with the idea of you finish this tutorial, but just to go a bit over the code and get the idea of what is needed to do. And then I think if you want to do it in the afternoon, well, you can do it, and if you want, you can post it on the Q&A channel, the values you get, and we can discuss. Then, okay, yeah, for me, I stop here in this part. I thank you very much for your attention in this session. And now at 11, Enrique will present the Lightning package. Okay.
Hi guys. Hope you can hear me well. So as Rafael was saying, we're gonna have a look on PyTorch Lightning now. I hope some of you at least are already familiar with that. There's an error. Maybe Rafael can have a look at that. But yeah, first, some people ask for the solutions for the ImageNet distribution notebooks. And for that, I decided to actually show you guys the official example from PyTorch on how they train ImageNet. I can send you the link after if you're interested. And it basically covers all we've done before for the regular distributed data parallelism, right? So if you see the script, it has everything inside, which is also good for showing for you guys. Normally, when you do a production code, you tend to divide things up, right? For example, here you have the argument parser, and you could put this in just a separate file as well. But yeah, anyways. So you have a bunch of hyperparameters that get parsed from the command line interface, right? We're not gonna go too much through it, but yeah, it's fine. And then on the main function, you have all this boilerplate distributed code. We saw that distributing with DDP is actually quite simple, right? But this is only the case if you only have a single setup with a single GPU like we have at Piz Daint. If you have multiple GPUs, to make it generic, the code can get quite complicated. And then if you go down here, there's another function, more abstraction for the distribution. Don't worry too much about it. I just trying to make a point for what we're gonna do later on. But anyways, these works quite efficiently. And later on, you get into the actual training, creating the data set with the regular data loaders, the ImageNet folder, image folder data set, right? So this requires you to have all the images in a folder. And we're going to convert these to DALI in a second. Right, and then you have the data load and data sampler, and eventually you're going to get to the validate and the train methods, right? Which are just down here. And you have your regular training loop with it's actually the same code I use for the average meter, right? And go through the forward pass, then update all the metrics, get zero degrades and backward step, and so on, right? And validate is basically the same. And then, well, there's some helper functions here to save checkpoints, which if you're doing real training, you have to, right? There's no way. Yeah, you need to save your work somewhere. You want to save it every epoch, for example, and do some smart checking on that as well. And down here is just the average meter, as we saw, progress meter. There's some scaling of the learning rate they do and the accuracy. Right, and that's it. So what I've done and I put on the repository is just a conversion of that. So it's exactly the same script with the arg parse, then the same boilerplate, distribution code, more distribution code. And eventually we're gonna get to the DALI loaders that we saw before. An easy way to show that is actually if you compare both of them. Let's compare selected, which I already opened it. And it gives the side-by-side diff. So we're just getting rid of the data, the torch utils data stuff, and adding your data loader, and all the boilerplate distribution code, and then the data loaders, and the data sets and data loaders and data samples that get replaced by the data loader that we discussed before. And that's basically, after that, I've added an additional parameter to actually save this to a desired folder, because otherwise it's quite unusable. Yeah, and we don't have to copy the data to the GPU anymore because it's already in the GPU from DALI, right? And that's pretty much it, right? This is the same code. Okay, to run this code, let me close that guy. You're gonna use the CLI interface, right? So you can't use the notebook. And you also have this convenient script on your repository as well, also on the ImageNet, where you basically set up all the variables that we discussed the other day, define just a checkpoint director, and then run your Python ImageNet with all the parameters you want, right? And this here is just to allow you to add more parameters if you want. So whatever you put to give to SPatch is gonna come out here as well. For a quick example, you basically do SPatch, and then I don't know if you can actually see that very well. I can't at least. So SPatch train ImageNet.sh. Right, and here you can give it additional parameters. I think like epochs is accepted. I think the default is 90 if you want to train for less. You can give it like here, and you can change the number of nodes like that, obviously. Change your account if you need to, and so on, right? And I think that's about it. Yeah, it has the thing ready. So this should start the job if I haven't done any mistake. Sorry, yeah, I do need to change the account. Let's see. Right, and this gets queued up, and oops. I already have a few jobs running, but this guy is being configured here now, right? Okay, so first so good. Yeah, if you have any questions about it, please let me know, but that's not too important. Now we can actually have a look on the Lightning abstraction. PyTorch Lightning, if you're not familiar with, it's just overlay on top of PyTorch. You can say it's just another abstraction that tries to make the training a bit simpler. If you're familiar with Keras from TensorFlow, it's something like in that direction. So in this notebook, basically the idea is that at the end, when you set up everything, you want to just really create your model and then train it, right? That's it. You don't want to have all that code, boilerplate code. And the way we're doing that is by, well, I put the model in another file. You can link here. Well, actually, let's go to code again. So in that file, you basically have a Lightning module here that gets the hyperparameters in the constructor. And in this case here, I also add the architecture. So the model is going to be basically Torch Visions .architecture, right? So you can test any different architecture that's provided by Torch Vision models. You could add more models, obviously, you can put your own thing. And then you have these convenient save hyperparameters, which basically save all your local variables, right? And this is exactly all the hyperparameters that we had here, so we don't have to repeat all this name. And these get saved in Lightning, and you can print them out. And this also gets automatically fed to the loggers that we can set up. I'm going to see after that. After that, well, the forward mode just forwards to the net that we defined, sorry. Right, and you do have to define your training loop yourself, which is different than Keras, where you have a standard training loop, right? But it's very simple, as we saw. You basically just get the data, feed through the forward pass only, no backward, no optimizers, right? You just need to really do the forward pass and then log metrics, whatever you want to log. There are a few different ways of doing that, but this is a convenient way. So here I'm also calculating the accuracy, right? And you also need to define, you need to define that for all validation, tests, and training steps. So I've refactored these into this step function. And the validation step just called step with a log prefix of val, and test, and the training the same. Training does additionally some optimizer parameters like the learning rate and the momentum, if it's available. But yeah, let's not worry about it. You have to configure optimizers, right? And basically define one optimizer that you want. You can have a learning rate schedule as well that also goes with the optimizer here, and you return them as a list like that. Define your data loaders, go for train and validation. And this is the basic data loader that we saw before. I'm using the same file still, right? You can grab the hyperparameters and pass to them, and that's pretty much it, right? This is our Lightning module. I have another additional helper function here to do the arg parse, right? And once we have this, we can actually do the training. So this script is self-sustained as well. So if you actually run as a script, you come here where you actually instantiate the model using the arg parse parameters, print the summary and the hyperparameters. Actually, I didn't do that. And I'm also going to use a few helpers here just to demonstrate some of the stuff you can do on Lightning. Right, one is the weight and bias logger. If you guys are not familiar with the weight and bias, we're going to have a quick look after that. It's just like TensorBoard Dev. It has a web API, and this will automatically submit all the training results to the API, and you can follow this offline, right? It's kind of nice to see. You also have some additional stuff to get the gradients and parameter histograms if you want to analyze your models. We set up a checkpoint to a root folder in Scratch, and then we can run the trainer, right? Let's go back to the notebook where we have a simpler version of that. So to run in a single node, it's quite simple, right? I'm going to define a module here just with a simple set of hyperparameters with a very small ResNet, and the optimizer that I want, and some batch size, and so on. I print the summary just for the sake of it. If you're not used to Torch info, it's actually quite cool. It also estimates the amount of memory that the model is going to use with that given batch size for the backward propagation. So this gives you a good estimate before you actually run the model that you're not going to get out of memory. This is a bit too optimistic. So you definitely don't want to have 16 gig here, or you will eventually run out of memory, because you have all the cachings and also the input they get loaded twice from the cache and the new version and so on. And we also have the data loader that's using quite a bit of GPU memory too. If you see, if I run this, right, by just instantiating this is running. Yeah. This instantiating model, agora you're gonna see some GPU usage, right? Because of the loader and the model. So here we have about 20% of the GPU is already used, right? So yeah, you need to do the rest with that. And then the trainer is very simple. For a single GPU, all you need to give is the number of GPUs. So it's aware that you have a GPU. Yeah, I don't know if it actually detects by itself. And I'll have to disable the sampler because in DDP with automatic, actually for a single GPU, I didn't need to have that. Yeah, sorry. Well, yeah, I'm just gonna define a directory to save the checkpoints and the logs. And that's pretty much it, right? I'm adding these guys here to make the training faster just for the demonstration purpose. And I can train this again. And you can see it has a nice progress bar with all the metrics that we defined before and so on. And to distribute that, it becomes really simple now because Torchlight supports several distributed strategies. We're gonna use basic just DDP because we only have a single GPU. But if you had several GPUs on the same node, you could use DDP2, which is a combination of data parallelism and distributed data parallelism. Well, it has some implications. DDP is generally the best option for most cases anyway, and it's the default strategy. I think if you actually just put GPUs 1 and nodes 2, it's gonna default to DDP anyways. But basically, you just need to put the strategy DDP here and number of nodes larger than 1, and the trainer will automatically find out that we are using this lerm as well through the environment variables. So you don't even need to define the environment variable that we're defining before. I made an SBatch script for running the script that we showed before, the train ImageNet PL. And you see here, I only have the optimization nickel environment variables, but I don't even need the master address and the master port and all this stuff anymore, right? It works out some default configurations, which works for us as well. So all you need to do is give in this case, the data set and the root direction in Scratch, and that's it. Obviously, you can pass more parameters as well. And the distribution is done, right? So it's a very, very convenient way of organizing your model in a way that would work in several different hardware configurations. If you do not have, if you're just starting using PyTorch, you do not have your code yet, I would probably recommend you to have a look at Lightning to start with. It also supports mixed precision, that we were discussing yesterday. And it's also extremely simple. Basically, all you need to do is do precision equals 16, and it will automatically use the native Torch AMP, automatic mixed precision, for you. I don't know if you have enough memory, but yeah, you can test this right here. I don't know if it's gonna work with the model they already started, but it looks like it does. Yeah, and you see it's gonna say it's already using the 16-bit native automatic mixed precision. You can change that to Apex by just adding the Apex backend. The disclaimer here from PyTorch Lightning is that they adding a lot of these features constantly to the framework. So if you are using PyTorch Lightning, make sure you recall which version they're using. because it can be a new version might break some of the old code. They do not have very good regression tests. But yeah, they do have some really interesting features. And one of that is the deep speed plugin that Rafael was explaining before. And to use deep speed with Lighting, you basically just have to set up the deep speed plugin. Well, the easiest way is actually to just give you as a strategy. And stage 1 or 2, you have to use mixed precision to use that. And it should already do all the casting that Rafael was explaining before for you. All right. It has some limitations on which optimizers you can use. I think you have to use the Apex Fused add-on for some of the stages. So yeah, you need to do some testing. You also have the full version. If you actually instantiate the plugin and give it as a parameter, you can add more options here. And yeah, to run it, as explained, it's the same thing again. You can run this script as batch in the same way they were doing before, right? And I submit the job and start it. That's me. And you saw before that I configured the weight and bias logger, right? And the watch. And you give that as a logger together with the checkpoint callback. And there are additional callbacks that you can use. And when you do the weight and bias logger, well, it requires you to log in the console, but it's just basically doing WMD and B logging on the console, and it's going to ask for your API token. And once you do that, it's going to automatically create a project for you, and it's going to log the whole training as it goes, right? You see, I still have some jobs running. And this is a job I ran yesterday night. Yeah. And it has some interesting stuff. It's just like TensorBoard, if you're familiar with that, right? Yeah, and it keeps updating itself. You can also configure to save artifacts. So you could save the best models on weight and bias as well. There's also other loggers where you can use just the regular TensorBoard, which is the default one. And then you can have a similar interface on TensorBoard Dev. And all right. Yeah, do you guys have any questions? I'll give you guys some time to play with the notebook and the scripts. And please let us know.
I have a question actually. So for the weight and bias logging, if I remember correctly, is that public? So are do those records become public?
It is, in this case, it's public unless you have an account with them. Or yeah, I think you have to pay something. I think it's the same for TensorBoard Dev, right? Which is also yeah, it's basically the same. I'm actually, yeah, in this case, because I defined the weight and bias. Sorry. Yeah, it's basically the same, right, as the TensorBoard. So you would, yeah, the TensorBoard Dev, you also would have to pay, I think, if you want to have a private one, or maybe you can have a private. I'm not sure, sorry. But it does save the TensorBoard files anyway, and you can open them on Jupyter regular. Just put the path on Jupyter or even on your own laptop, right? By using the TensorBoard. It's just convenient here for showing purposes because I can share that very easily with other people. But yeah, it's the same case as the TensorBoard Dev. Any other questions?
Thanks.
Yours. All right. So I guess we'll leave you guys to play with that a bit, and please let us know if you have any other questions, any other issues. And yeah, we'll be around until the end of the afternoon, as Rafael was saying. So stop sharing now. Yeah, please let us know if you have any other doubts. And it was great to have you guys here. Thanks for your attention. Have a nice day.